Hello, please. Can you see my cursor moving?
Yes, please.
Yes, Doc.
Okay, so this is what we call bauxite. If you have if you by accident chance on that, I'm sure you throw it away. But that is where we extract aluminium from. Um, so that's bauxite. Then we have other ores like the beryllium aluminum silicon oxide, berry. We have the chrolite, which is the sodium aluminum fluoride, which is that. We also have the alumina, some call it alumina, some call it corrodium, and those kind of so. But then it's there's aluminum oxide, nice corrodium. Of course, we can have other crystals which aluminum can be forming nice crystals. We can design that from aluminum. So basically, what it is, so this is we have the natural corrodium, that's aluminum oxide, and then we can have the synthetic one that also looks like the corrodium, like this stone. We can synthesize that as well. So we have the natural and the synthetic form. Now, bauxite is deposited in our soil in Ghana here. So we can have a lot of this deposit in Awaso, Chebi, Ninehi. I think this is the three main towns that have aluminium or the bauxite deposit there. Ninehi, Chebi, and then the Awaso deposit kind of site, and they mine it in this, like they call it the red soil, where they mine it and then they extract. They just get the aluminium or the bauxite in this form, and then they export that. So most of the times when you go to set towns, they have these stones that they have piled up where they are trying to sell that. But beneath this heavy soil, we can be getting that. So if you look at it, it's stated that the local officials have estimated almost like 350 million tons of bauxite, which it's supposed to be leaving the the shores of Ghana every kind of year. But um, normally our focus is on gold, so we don't pay much attention to that. But I think that is something which, so this is our so which is a bauxite mining site, which is still ongoing. They are still manufacturing, or I mean, mining those bauxite as well. But however, you can see, I don't know if my video is going to play, but then we still have the mining going on. And as I said, our focus is not much on the bauxite, but then this drone footage showing the portion of Ayawaso bauxite mine somewhere in September. It was captured last year, September, and that can still see the Ayawaso village. And in that forest, people still doing mining of this bauxite. And you can clearly see how the mining has really caused our forest. So it's not only galamsey, I mean, the gold that is causing our forest, but then other mining like the bauxite mining has really caused our forest. I guess maybe you are following the video. So this is so it's now showing the pathway to that mining site. So here is a mining site. So clearly you can see the damage that as a portion of our soul has really been. So, and it has even come closer to the city now. Okay, so just at the backyard, yeah. So this is the mining company and how they have mined the bauxite and the havoc that has caused to our forest now. Okay, so I'm just showing you what mining has done to us, and of course, so if we're going to be damaging our environment to this extent, my opinion is that we should rather be benefiting, even when we are destroying our environment. But that is what has happened so far. Well, that's aluminium for you. Now let's look at how we extract or we get our pure aluminium. Okay, so the extraction is from the ore, like from aluminium, the bauxite, aluminium hydrated aluminium oxide, which you call bauxite. Then bauxite is one of the most abundant ore in the world. In the world now, where we extract the bauxite, aluminium from bauxite has been one of the most important or the most abundant source for aluminium. And of course, we have some here. But then if you are looking at countries that have large deposit of bauxite, then we look at Jamaica, we look at Brazil, we look at Guinea, China, and then India. These are the countries that have large deposits of bauxite in their soil. That, as I mentioned, sometimes we'll get it in some form, like the aluminium oxide or the aluminium hydroxide form. So the main ore where we extract aluminium from is the bauxite. Now we get to have the extraction. I'm going to look at how we do the extraction, where we add a base to the sand. Of course, we break the rocks of that bauxite that we have mined, break it down, and then we add a base to it so that we can convert it to a silicate. But then we'll try to purify the aluminium oxide, which is a bauxite, other known as the alumina. Okay, so the purification, basically that's the principle of we trying to know that the bauxite contains other kind of impurities like iron oxide. Almost like 25% of iron oxide is there. We have silica there, that's sand. Sometimes we can also have, so silica is like 7%, then titanium dioxide also like 2 to 3%. So what we do is that we're trying to purify the bauxite before we extract the aluminium. We'll turn the bauxite into a powder. We'll mill it into a powder, and then we'll add almost like 10% base. That's a sodium hydroxide solution. We just add that, and we try to heat it under a little bit pressure. Then when we heat it, our kind of focus is just to see if we can really use the base to what we call digest. So the base is going to be binding itself to other acidic related component there, so that we can release just the aluminium just like that into the solution, and then we'll get to have that. So the next step, so first we'll get the ore. The second, we'll try to purify that by adding the base. The third is to synthesize what you call the chloride. That's the sodium. So when we add the sodium hydroxide, we are assuming we can have to, we can be producing the chloride, which is the sodium aluminum in the system. So sodium aluminum fluoride, or we can just have aluminum fluoride in there. So we'll try to synthesize this fluoride, and the key method that we use is just to use electrolytic reduction, so that we put electrons in there, then that will be, targeting the aluminum, so that we can electrolyze this element there, the aluminum, so that it becomes the aluminum solid in that form. So that's how we try to synthesize the chloride. And of course, at the end, we release aluminum in the halide of aluminum in that form. Then, so that's a fourth step there. So the electrolytic reduction to just form or produce the aluminum, the pure aluminum in this particular form. So that's how we produce the aluminum in that form. Of course, after that, they'll just preheat or heat it again, and then begin changing it into various, whether a sheet or tubes, so that it will be ready for exporting. or in our case, we would rather be importing that into our country so that we can now start changing them into that. So that is just aluminum. So all that I've said is in equation form. So they all, you heat it with a base to form the silicates, then the base again goes to react with the aluminum and form the unstable, and then of course it's also going to be engaging the bases, I mean the acids, Lewis acids there, so that it will not affect the aluminum oxide. Then of course when we heat it again, we'll form the aluminum hydroxide now, we'll be forming the alumina where we can filter it and just get it clear. So that's one step of getting our pure aluminium. Another process is to use the Hall process. So that's the method which I just so another method of extracting the aluminium or obtaining the aluminium from the bauxite is to use the Hall process. The Hall process is just of course the ore again which we use for the aluminium is a bauxite, and then the purified bauxite again. Of course, we continue feeding the system with that purified bauxite, and the purified bauxite basically we add in a base to that so that it gets rid of the bases that are in there, so that we can get to have a purified bauxite. Then the chloride will be synthesized. The chloride basically is sodium aluminum fluoride, which will be synthesized. And of course, with pushing electrons in there, we can then separate the aluminum in the form of an halide. So aluminum fluoride can be separated, where when we heat it again, then we'll get to have aluminum oxide. Now in the whole process, the electrons, the electrolysis, basically we use a DC current to just pass through that. So we just connect the device to a kind of a DC current where we push the electrons from the electricity. So the electrons go there, and then will form the molten aluminum oxide, which will then be sinking under the tank. So that's the whole process. Let me state that there are two general rules when it comes to electrolysis. Now, in electrolysis, we are basically dealing with release of electrons either from a source, either from a cathode or from between a cathode and an anode. So when we have metals in the system, metals or hydrogen in the system, you see they will be forming the positive kind of ions, whilst the others, where the anions, I mean the non-metals, will be forming the anions. But we note that when we have an electric current, or we have a cathode and anode kind of point, a positive and then a negative, we'll see that the metals which are positively charged will be moving towards the negative cathode electrode, whilst the non-metals, which are the anions, will be moving towards the positive anode electrode. So we have two electrodes here. The positive part we call the anode, that's the electrode, then the negative is the cathode. So all the metals in the solution or the hydrogen will be moving towards that. So you see that that electrode will be expanding in size, which we can scrape off the metal depositions on that electrode. Then the anode will be having the non-metals. Of course, that will not be interested in that non-metals. But when we remove the cathode, so assuming the cathode electrode was like say 5 millimeters, when you take it through electrolysis, you see that at the end it expands and become like say 7 or 10 millimeters. What it means is that there have been deposit of metals on the surface, so we can just have those metals away. But that it cannot be like on commercial basis, just a small kind of metals can be scratched from that electrode, and then we use that. So that's what we can be getting from the redox or electrolysis, and that's what we call the Hall. So some say Hall Harat process. But another process where we can be, extracting aluminium, which is quite simple, and that is the setup which was set up for us, I think by Nkrumah, is a buyer process. Very simple process, but then I don't think the system is working here. So the buyer process basically starts with, um, it's just following the whole Harat process, but like an invented kind of form. Okay, so we have the alumina, or what you call bauxite, and of course we crush those bauxite, mill it down. So this is just a simple system there. Mill it down or crush it more with a miller. Then add a base to that, and that's where we are trying to purify the aluminium there. And then we add some binders, the lime to that calcium oxide, and then we'll filter it. And when we filter, we'll get the residue, and then we'll pump the residue like a reddish mud out. And then we'll get to have, where through that filtration, we'll get to have the aluminium oxide forming a precipitate. Okay, so it will form the precipitate here, and of course in the solution form. So basically, we can have the aluminium oxide, aluminium hydroxide, which of course we calcinate it, and then we'll form the alumina, which is the aluminium oxide. So I should say that we don't have like just aluminium metal, but then normally they are always coated with the oxygen. So the alumina is what we have there. This is the scheme for that production which I just mentioned. So from crushing, put a little bit base pressure it, then filter that so that there's a muddy. So the video that I show you, that's just a muddy kind of form. So we are supposed to be doing this. So once we add this, or we get this sodium aluminum hydroxide, we begin forming the crystals there. And of course, recrystallization is rotary. Using rotary will form the aluminum oxide, which is the pure form of the aluminum which we use for in the industry for other kind of stuff. So that's the buyer process which we use. But unfortunately, we don't go through this to produce the aluminum oxide, but then we only get the finished product of the aluminum oxide and then convert them into the various shapes that we want, like the saucepan or the cooking pan, the roofing sheets, and those kind of stuff. It's quite interesting that what we can create, we cannot destroy, like matter. We cannot create, we cannot destroy. So aluminum has been an issue, which I think now people are getting into the aluminum recycling. And this so-called GAO people, they are making a lot of money, but we don't respect them. So they come and create a small harbor there. Later, by the time you realize their harbor have grown to become big, and they are now selling. Of course, some of them combine the rubber product, so they also get the rubber and sell them to the rubber companies that convert them to the plastic chairs and those both and those. But then the aluminum recycling is also quite lucrative. Really making millions from there. So over 50% of the aluminum that we have can be recycled from scraps. And I think I've forgotten the person who says that he first made his million pounds from just this scraps. So who is that? Please, if you have heard that, maybe you can draw my attention. Is it this politician? Caesar, Freedom Caesar or something. What's the name? Bediako, yes. That's her name. So just by selling, yeah, Kwame Diapo. So they make he made a lot of money from just selling scraps. Yes, thank you very much. So at least aluminium recycling is quite lucrative now. Some of us in this part of now we see these kind of people going about cutting aluminium, the iron rods and those things. They'll just be cutting them, just just to go and sell them. But then that's it. I just brought into that we see that we can still be recycling the aluminium. So you don't just be throwing your aluminium cans just like that. If we really mean business, we can really do that. But what we need to understand here is that somebody raised their hand.
Hello, Doc.
Yes, wisdom.
Yeah, it's about the processes of extracting the aluminium from the bauxite. It's like you talk about
Okay.
the whole process and the Bayer's process and the rest. But are they independent processes? Because I think that, or they are just stages, and each stages involve those. Because I know that when you're extracting, what in other books that we read, if you're extracting aluminium, you need a concentration stage where the aluminum be purified, and the concentration stage is where you have to crush the bauxite, add the base to it to form the complex, and then when the complex is formed, then you form the pure alumina. Then after getting the pure alumina, then you send it to the purification stage where the distance you use the electrical process to get a pure aluminium. But in this case, like you have separated the distance, the stages, that this is another way of extracting the bauxite, and this another way, and that is confusing me now.
Okay, so I've given you at least three ways of
Yeah, that's my
extracting
view.
aluminum oxide. Now, each processes have steps that you follow. Is that okay? So, for example, if I take the Bayer process, it's different from the Hoharat process. Okay, and that's each of them has its own kind of steps that it follows. So, if I take the say, for example, the Bayer process, which I'm just showing the scheme here. The purification of the bauxite basically means that the bauxite which we mine contain other elements like, as I mentioned, like iron. So we have iron oxide there, we have silica, we have titanium oxide. Now we want to separate them. Okay, so we go through steps. So we'll purify that by just separating so that we get bauxite, aluminium hydroxide. I mean, aluminium oxide, hydrated aluminium oxide is what we call bauxite. Al2O3, then the water component comes in. That's what we call bauxite. But then when we mine the ore, it contains iron oxide, it contains sand, then it contains titanium oxide. So we need to separate this compound. And that is where we'll crush it into that powder. Then we'll treat it with a sodium, a base. Now the base is going to be targeting the acids in there. So that's where we begin doing the purification. Is that okay? So the point is that we have various ways of doing or extracting the aluminium oxide. Then when we get even the aluminium oxide, we can do recrystallization to get a pure aluminium oxide. So there is difference between the Bayer process, a difference between the Cronut process and then the or Harat process. Is my mind making sense?
Yeah, you're making sense, but it's like other material that we read is what is confusing us now. Hey.
So bring out your confusion and let's address that.
Oh, my confusion is that it's like in the material that we read, they will tell us that we have the stages of extracting the aluminium, getting aluminium oxide.
So each
And
stage differs from
hello,
the method that you are using.
hello.
Wisdom. So each
Oh,
stage will differ from the method that you are using. Can you hear me?
hello. Oh,
I can hear you. I don't know about others.
I can hear you now. Yeah. Yeah, Doc, I can hear you.
So, yes, I'm saying that each of these stages will depend on the process that you are using. So if you are using, say, the buyer process, it goes through stages. If you are using the whole Harrat process, it also goes through processes. I mean, stages. You get me? So here we will start with the what they call the washing process.
Okay.
And that is when you are, in other words, you are trying to say that you are doing the concentration of the aluminium. And the reason is that the all that you mine is containing other components in there. So you need to wash away the impurities from that.
Okay.
So that's the first stage. So irrespective of the process that I take, the whole Harat, the buyer, I need to do that kind of concentration process. I mean, step by washing it. Are you okay? Then I then look at which process I'm using. If I'm using the buyer process. So in the buyer process, what I'm trying to do is that I have bauxite, and bauxite is more or less like an impure aluminum oxide. And then I'm changing it to a pure aluminum oxide. That's a buyer process.
That's the buyer process. Okay.
So a bauxite is aluminum oxide, but now I want to get to have a pure aluminum oxide.
Okay.
Is that okay? So that's a buyer process. Now the whole Harat process is just having aluminum oxide, but just want to extract only pure aluminum metal by using electrolysis.
Okay. Okay. So now I get it now. I get it now.
Then we have the hope seeds process where that again, I want to get a pure aluminum metal from also the bauxite that I've there. So that's a process. So if I should go back to my slides. So there's a process which I'm just trying to show you here. Okay, so extracting that, I need to do the washing where I add the base to that. Okay. So if I'm taking the buyer process, I'm going to, so bauxite itself is aluminum oxide. So at the end, I'm going to be forming a pure aluminum oxide from the bauxite. That's a buyer process. This is what I'm showing you. So the bauxite here is impure aluminum, but then at the end, I form aluminum oxide. Now the Harat is just trying to tell us that I'm having the bauxite, but at the end, I'm going to use electrolysis to only extract pure aluminum metal, molten aluminum metal, which is going to be drawn towards the cathode electrode. So I'm going to scrap that from the electrode, which is going to be attaching itself to the kind of, the cathode, the negative part. Okay. So this is the fence. I don't know if you can see it. And so we'll see the aluminum depositing on the negative electrode, whilst the non-metals will be going to the positive part. So that's the process of extracting the aluminum.
Yeah, Doc, I've got. Thank you very much. But my another question is that when we were listing the ores of the bauxite, we saw that we have the alumina, which is the corundum.
Bauxite itself is an ore. So clarify the question again.
Yeah, when we were listing the ores of the aluminium.
Yes.
Yeah, we saw the corundum.
Yes.
Which is the aluminum oxide.
Yes.
Because in the process that we are going to now, our aim is to get aluminum oxide, which we will take to the electrolytic process in order to get the pure aluminum. So if we have an ore which is aluminum oxide, then why do we use the bauxite as our chief ore? While we already have aluminum oxide or which you can just mine and then take to the electrolytic process in order to get aluminum. Why do you go for bauxite and then instead of the corundum?
Okay. So but you are aware that the bauxite itself is even aluminum oxide,
Hydrated aluminum oxide.
but it's just containing water. But then, so
Yeah.
let me explain that. Okay, so aluminum oxide can exist in different forms. Okay, so aluminum oxide, which the collodium is also known as the alumina. So another name for collodium is what we are calling alumina. So we can have what you call, two forms of these aluminum oxide. We can have the alpha alumina, which is what we call the collodium. Okay, then we can have the gamma alumina, which is what you call the activated alumina. So though it's an alumina, but then the pure forms is what will make us look for which one are we trying to. So the alpha alumina, which is the collodium in itself, of course, can be pure, but then it comes in the form of a rock. This one. So this is collodium. And this is not what you are interested in. So that's the alpha alumina, the collodium. Can you see my picture? Okay. Then
Yeah.
we want normally what we are using is the activated alumina, the activated one, the one that can easily be protected by the oxygen. That's the aluminum oxide. So which that's what we are calling the pure aluminum. So aluminum which has been coated with. So that's the gamma alumina, which another way we call it the activated alumina. Okay, so the pure aluminum, which we are going to be extracting so that we use that in the formation of our cans, and those we normally use the activated alumina instead of the gamma alumina, which is the nice crystal this way. So the collodium is not the pure aluminum which we want to be using for our can. It comes in the form of a rock. Are you okay? Can I proceed? Okay. Yes. So that yes. So, yeah. So the recycling of that. Well, we should say that aluminium is quite useful. For example, outside our system, we don't need aluminium in our body, but then we use that also. So we should just so basic properties of aluminium. We see odorless, of course. I don't know who tasted that to make it tasteless, but then if you try to chew aluminium, I'm not sure you get that. But then it has this high thermal capacity in there. But then it's a good way to really, of course, when it gets into contact with heat, you can really see that it just melts. So a higher kind of temperature can really melt that. But then the point I want to make here is the interest in trying to recycle our aluminum so that we save millions of. I mean, our environment can be clean and quite okay when we are doing this aluminum recycling. Somewhere else, I know, for example, if you buy a can of Coke or a malt, then the cost of the aluminum can is added to the Coke that you are bringing. You are going to drink. So that after drinking the product, you bring the aluminum can for recycling. So if the can Coke is say one cedi 20%, the 20 pesos is for the can. So when you bring the can back, you count for your 20 pesos. And that's how their country is neat. So they are cautious of the recycling because they know they are going to be making their money back. But here in our part, we just dispose them anyhow. And it's quite kind of a um, worried how our environment is quite polluting with this aluminium. And it's not biodegradable. Aluminium cannot be degraded in the soil. So it can be in the soil for quite some time and it will not degrade. But we can do the primary recycling or the secondary recycling from the aluminium cans that we have, or mostly from the aluminium product that we have. And so we'll see that, well, I've considered the properties used for lightweight food industries and those kind of stuff. Now, talk of alumina. Alumina is also quite a useful kind of compound. Now, well, I wanted to, okay, maybe your attention didn't go on. Well, so I've considered the properties or the reactions of the alumina or aluminium oxide. That's the three plus three. So aluminum is in the plus three. And so in terms of reaction, it can react with oxygen to produce the aluminum oxide, which is the alumina. And again, I should mention that alumina can have three phases. We have the alpha, beta, and then the gamma, different phases of this alpha, the alumina. So the alpha, which is the collodium, which is basically coming from the nano level. So white is crystals forming a powder form. That's what we call the alpha one. Then we can have the gamma, which is the activated alumina, which sometimes it's where we can produce other forms. So, but then we can have the aluminium compounds like aluminium chloride reacting with water and reacting to produce that aluminum hydroxide, which is amphoteric. But there's one thing that I want to draw attention to is the alum. So alum basically is just aluminium metal combining with the group 1 metals, and then so the sulfate of aluminium plus group 1 metals, and then um, the hydrated form. So the general formula for alum is M plus 3, the sulfates, and then the hydrated form. That's what you call the alum, aluminium sulfate. In other words, alum. Where the M plus is it can be potassium, sodium. Commonly, it's potassium and sodium. So we can have the potassium alum, sodium alum, or sometimes the ammonium alum. Then the alum basically, so if you look at it, depending on the plus 3 metal that we are using, but the common that we use is the aluminium for the group 3. So we can have the aluminium alum that we have. Now, each of them plays a particular role that we use. So the aluminium-based alum is quite useful, very, very important, especially in the industrial process. Mostly, the widely used one is a potassium alum. And they use it for flagellants. And so for kind of liquids that have kind of a high turbidity, when you add alum to that, it's kind of flagellant. It settles those particles that makes the liquid turbid, so that it can really settle down. So in our turbid kind of water, we use alum in treating those turbid water. Now, I think, for example, in our case here, which the Galamsey situation, the alum we need to be buying more, and again, its stability is quite um, not okay for drinkers. So I think the government is resorting to other, like using other nano stuff to absorb the turbidity. But the potassium alum is, I think they sell it. They sell it in the market where you can just buy it, drop in your turbid water. It just get settled for a clean water as well. You can talk of dyeing companies, deodorants. We can have alum in those deodorants. We can have baking powder. You can have a little bit alum in there. Yes, I've heard kunu, somebody raising their hand or something.
Okay, Doc, please, when we were talking about the alums, the examples of the alums, You used only the group one metals for the names. Is it that the the name when the potassium when you're using the sodium and the aluminum, it is potassium alum, and then when you're using the sodium and the aluminum becomes the sodium alum. So you don't consider the chromium and then the aluminum and the iron that you are using.
No, so when you are going to be using chromium, the name changes. It's no more alum, but then it works in the same properties.
Okay.
Uh, but then if you are using aluminum, that's M3, that's where we have the alum, aluminum base kind of alum. So if you are using chromium, then we can say chromium base alum, but then it has the same kind of structure or the same general formula. So we have the aluminum base, meaning it is the M3 here is the aluminum.
Okay.
And that's what we use normally when it comes to food related or those.
So when we are asked to list maybe some three examples of an alum, are you supposed to write potassium based alum and then sodium based alum, or we write potassium alum and sodium alum and
So
maybe
if you want
ammonium alum?
it's because if the M plus there is potassium, then it's a potassium alum.
Okay.
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 And then if the N plus is say sodium, then it's sodium alum. But then if the you want to change it and make it the say chromium base, then we call it chrome alum. It's not just alum, but then chrome alum. So
Okay.
that would be potassium chrome alum if you want the name. So if you are using chromium, then we have potassium for the M plus. Where's my cursor? So I don't know if you so if M plus is potassium and M plus 3 is chromium, then we can say it's potassium chrome alum. But
Okay.
then if the M3 is aluminum, we can just say potassium alum. Is that okay?
Yes, please.
Okay. So that we can have by changing this, we can have different forms of alum. So if I change the potassium to sodium, change the chromium, change the iron, we can have different forms of alum. But then I'm saying that the common one that we use is the aluminum base. We use that in the water treatment, we use that in the medicine, we use that in cosmetics, like in deodorant, you see alum in deodorant. We use that in food preparation, like baking powder. We have alum in baking powder. If we talk of these textile industries, we have they also use alum as well. So that's just the alum. Now, some of them look like, of course, some pharmacists or pharmaceuticals use that in the form of bleaching, or some again use that in perfumes, just as I mentioned as deodorant. So we have different uses for alum. So I've stated the general form, but then alum benefits sometimes they use in shaving those shaving creams so that we avoid these bumps in the deodorant, the cosmetics, so that pimples, black spots. The alum can remove those black spots. What is it? This arthritis, foot breaking can also be, we use alum there. Um, like water treatment to treat this stability, and it comes in this particular rock. I think some now have made it in a form of a tablet, which they are now selling. Okay, so we look at it in natural fat. Alum now become the powder form now has become like a natural antiseptic, inflammatory, antibacterial properties, and then those kind of forms. So that's the alum that we are using. A lot of benefit for that alum. Okay. Yes. Now, please, is that okay? Okay, no hand, yes. So in that, we can see for general use of aluminium, we can see that we use majority of them is used in the automobiles or the aircraft. We use that in building, in the engineering, and of course, packaging as well. We use aluminium in there. It's quite interesting. Now, for example, in CPUs, the graphic processors and those stuff, these are pure aluminum kind of forms. Our body don't really need or uses aluminium. And so if we chance on having heavy aluminium exposure, then they are going to be on the depositing on the skin. So they'll just depositing on the skin, which it can find itself into the skin pores and begin blocking those skin pores. So aluminum is not required by us biologically. We don't really use aluminum, or living things don't really use. So there's no scientific evidence that we use aluminum. However, when we get exposed to aluminum, we really have an effect, especially skin related effects. We can really have those effects. So that's aluminum. As I mentioned, the compounds of aluminum, will see much of it related to the compounds of beryllium, and that is why aluminum finds itself in the P block, but then it's a metal. So it finds itself here, but then it has a close relation with the um, beryllium. Now we'll look at the post-transition. So when we get one step down, we'll look at the gallium, indium. These are post-transition metals. So they are transition metals that finds themselves in the P kind of block. So we're looking at gallium, and then indium, and then the titanium in there. But gallium is very soft in metal, at least with a very low temperature, as low as 27 degrees, it also begins melting. So highest like 30 degrees, usually it melts. The melting point of gallium is 30 degrees, begins melting. So sometimes we use that as sensors, or in these thermometers that we have, we will to just melt just like that. We see much of gallium usage in solar cells. Okay, so we have gallium in there, and again, we'll use gallium a lot as a semiconductor. So we add gallium with copper or gallium with sulfur to produce this gallium kind of system. So that's gallium. Reactions of gallium, we'll see that it can react with oxygen, can react with water, can react with acids, and then bases. React with oxygen to form the oxides, react with water to form the oxides again, then the acid to form the halides, and then with a base to form the hydroxides of that base. Again, in terms of uses, we don't have any biological use for gallium, but what we know is that it's quite useful in solar panels. Use that also as semiconductors, and also readily helps us in combining other metals as well. It has a low melting point, and so we can be using that as in sensors where if the temperature rises, then it breaks, and then there is going to be water spill. So this is just what we know gallium to be like. The next element is indium. I'm just going to in just taking those. Indium basically, again, is quite soft, but of course, again, we don't have any biological use for that. But then indium is just I mean, the screen covers which you have, or the so-called screen protectors of our phones. That's what we call indum. So it belongs to that boron group, but then it's quite a metal that can be transparent like a polymer. So the correct, for example, I'm sure you people, I mean, we are aware that we can have phone screen protectors where um, some are quite durable than the others. So they're not a plastic one, which any small crack can even crack and go and crack your the original kind of screen. We have correct screen protectors, which is some of them having the reinforced indum kind of form. Okay, so that's indum. Well, initially, I don't know if you have seen this, where I think now people think that when you do your teeth like this, it's for fun. Please, it's never for fun. It's just for correcting the teeth. Okay, so indum is quite non-reactive to a biological system. So they use that to correct the teeth so that all gaps will be kind of closed. And after that, it has to be removed. It's not for fancy kind of stuff. Uh, that's to be removed.
So I have a question.
Sorry?
Hello, sir.
Yes, sir.
Hello.
Yeah, I can hear
So
you.
please, this teeth, is it bracelet or something? Does it have effect on the body?
No,
Can this cause
it's
skin cancer?
no, please. It's non-reactive.
Oh, okay.
It's not reactive. But then the thing is that it serves as a purpose. So after the purpose is served, it should be removed. But it's not going to react
Oh,
with
okay.
the system.
Okay.
Yeah, so there's no
Thank you, sir.
biological kind of effect, whether it's toxic or non-toxic. So we don't have any. I think at a point, people who want to fancy it, instead of using the indum uses, I heard somebody saying that it's diamond, but I doubt if you can buy diamond on your teeth like that. But this is just an indum which they use to correct. In the metal which they are connecting it, the stainless steel metals that they are using, but it's non-reactive. It doesn't react to the system. Okay, so that's indum. Now, when we talk about the reaction, indum can have oxidation state of +1 and then +3. So we can have these two variable oxidation states where sometimes it can have the +1 state, sometimes it can have the +3 state. Again, don't forget that it's a post-transition metals. The transition metals, that's why we call them transition. For the main group metals, I mean the main group element, they have a fixed oxidation state. But for the transition metals, they have variable oxidation states. Some metals can even have like 7 different oxidation states. So it changes. So the post-transition metals also have variable oxidation states, and indium have oxidation state of +1 and then +3. So in their reaction, you can see it can react with water, react with oxygen, react with acid, and of course base. And the compounds will be the oxides, and then the halides, and of course the oxides as in the base oxides. Just as I said, there's no kind of biological rule when it comes to Hindu. There's no biological kind of system. But what we know is that they use it for this kind of places in there. However, we have seen that the compounds, so not just the Hindu metals, but the compounds of Hindu are really, so for example, the organic related compounds are really toxic, but not the metallic Hindu. Okay, so Hindu compounds really can, if it forms compounds, can really go to the point of attacking the heart, the vital organs in the system. Hindu can just go there and attack them. So the heart, the kidney, the liver, and those stuff, we can really attack that. But we don't know, or we don't have much information as to whether the system uses that or not. That we can't really tell. Well, environmentally, we are still looking at how Indum affect the environment. But what we know is that we use it for screen touches, your screen touches there. I think the last time you remember the color which comes from our screen is what element? Can somebody reminds us? Is what
Strontium.
element?
Strontium.
Protein. Okay, thank you. At the screen here, we are seeing is Indian. We'll see, please, if you need your mic and at some toy cars and some sensors as well. Polata. Okay, thank you. Okay, so that's what we know in Doom 2. Now we get to another post-transition metal, which is a titanium TL, atomic number 81. Well, here we'll see that it's quite gray, the post-transition kind of form. But here, this element is toxic to our system. It resembles or behaves like tin, but then it's extremely toxic. So initially, we didn't also know as we were growing that as science was growing that we realized that mankind was dying from titanium. But then initially they were using it for medicine. Okay, so later they saw that no, it's rather intoxicated and can kill. So titanium is tasteless, it's odorless, it's colorless, but highly toxic. Okay, so later those that want to be committing suicide, they have those used in suicide medicine, the homicide uh, medicine, and some illegal abortion. So titanium was initially using as illegal abortion, goes to kill the fetus. But then we discovered that after killing the fetus can even kill the mother itself. So it's quite toxic. Well, when accidentally exposed to titanium, after say an injection in food and those stuff, we should note that it can really kill you within some space of time. Okay, so just a small dose of it can really go to. So later they were using that as a rat poisoning. So can easily kill that rat and those stuff. But we have tanion used in our motherboard, that's an electronics. We can have that. So this is an example of somebody being exposed to tanium. So the news is going off or is going off slowly. That's tanium poisoning. So you see that the compounds of tanium like tanium sulfate, we'll see that was used as a rat poisoning. Now it is said that the tanium sulfate is extremely poisonous, like more than a venom of a snake. So how fast it reacts, they compare to the venom of a snake, and that the tanium reacts faster than that of a venom. Okay, so at least if you come closer to titanium sulfate, you should be very careful. You don't get closer to that because it's a lethal dosage. It's quite extreme. Now, if you just get to any of the titanium compound, you begin experiencing the titanium poisoning, where there'll be hair loss, your skin be reddish if you are fair, and of course, gradually you will just be losing the whole system, just like that. So that's just titanium. Okay, now the reaction again, react with oxygen, the acids, okay, and that is just the compound. Now, thallium is also going to be having oxidation state of +1 and then +3. So just like the Indu, so +1, +3 kind of oxidation form. However, we still don't have any biological uses. There's no known use of tanium for us. We don't use any tanium, but we use it in production of these electronic devices, fiber optics, camera lens switches, and these closures, and that rat poisoning. That's we know that is quite used in this rat poisoning, and people use that as for attempting suicide. Yeah, in their homes, especially the tanium sulfate for rodent poisoning. And it's unfortunate that some, for example, some countryside hunters uses this poison to poison some kind of rodents like the grass cutters and those things. Then they'll bring it to the roadside and sell it. Okay, and the poison goes on. So they tend to poison people who who will be chewing that. But the funny thing is that we don't care. Once we are making money, we don't care. Okay, so the person will even tell you, oh, this is a trap. We just got it from there's a trap. Sometimes they also we got it from dog hunting. We got it from say gunshots. Meanwhile, they know that it's just they use poison in it, that and they'll sell and take their money and go. So we just know that that's what they were using for this rodent. Not much of apart from the small reactions that we have, but there's a few stuff that we can talk about. Kind of. Another element that we know is the tin, very common. Um, I mean, very popular as well. SN, meaning it is coming from the old name. So I think the SN is coming from the old name. Can somebody tell us what will be the old name for tin? Yes, why is tin is TIN? So why is the symbol SN?
I think that the other name for it was, I think, Stanley.
Come again.
What I remember is Stanley. I don't know if I'm
Stanum.
pronouncing it. I don't know
Yes,
if I'm
so
correct.
yes, that's correct. So STANNUN. Stanum. Stanum. Yeah, so that's the old name for tin. SN. Okay, so again you can see that's a silver metal which belongs to the carbon group. Okay, the metal that falls under the carbon, we see tin here. Okay, so we'll see that tin is used in combination with other metals to form like bronze, like with copper to form bronze and those kind of stuff. But we've seen the common property of tin. We said that it's widely used to replace the aluminum cans because, of course, aluminum is quite expensive as compared to tin. And then in terms of corrosion, tin, of course, aluminum resists corrosion. Tin also resists corrosion from water. So it avoids it being attacked by water. Okay. Now, when we take tin, we can have two allotropes of tin. We have the white tin and then the gray tin, two allotropes. Okay. I don't know if somebody, the allotropes, what is allotrope? If I say
Um,
allotrope, what do I mean?
um, the same element but different physical forms.
Okay, so different forms from the same element. So that's where we're at. So I was talking of the various allotropes of alumina, the alpha, gamma, beta, alumina, different element or different compound but different forms. The same element but different forms. So we have the white tin and then the gray tin as well. Okay, so please you note that. We see that for tin, Well, I've mentioned that it combines with copper to form bronze, and early in history, we see the Bronze Age. After the Stone Age, we came to the Bronze Age. The bronze before the Iron Age. So we'll see tin really at work here. Now, if you look at it, tin is having the oxidation state of +2 and then +4. So we have the tin 2 and then the tin 4, the stannous and the stannic. That's like ferrous and ferric, stannous and then the stannic compounds, the +2 tin, then the +4 tin. I think I mentioned that we can have two allotropes, the gray tin and then the white tin as well. That's the two allotropes that we have. We can react tin, or tin can react with oxygen to form the tin oxide, can react with water. So the tin oxide, it can react with, or tin can react with water again to form tin oxide. Then we can have the reaction with halogens, so the tin with halogens will become the tin halide. With the acid will so form the halide, and then with the base will form the halide. Yes, wisdom.
Doc, which one is the gamma tin over there?
The
You have gamma tin on your slide. Gray tin,
yeah,
white
yeah,
tin, and then gamma tin.
a mixture of these two we call the gamma, but that is rare. So the common allotropes, can you see my Kesa? The common allotropes is the gray and then the white. But then if they mix, we can have these two mixing to form the gamma allotropes. But that is quite a rare thing. It's not
Okay,
that.
so but the gamma is also an allotrope of tin.
Yes, we have gamma tin, we have white tin, then we have the gray tin.
Okay.
But then the most two common, I'm talking about the two common allotropes, is the
Okay.
white and the gray.
Okay. Okay.
So the gamma is also available, but then that is very rare.
Okay.
Yeah. And that again exists at a very high temperature. You can just even see at the white tin, the melting point for the white tin is 161. So this is almost at a very high temperature before we can get that. But that's a mixture of the white and the gray, but real kind of tin there. Okay, so the reactions I've mentioned them with oxygen, with water, with the acids, and then with the base. So again, you can just see the common reaction pattern that goes around. And so now let's try to educate ourselves with what we call tin poisoning. It's very common, but then we don't really pay attention to that. Now, we should note that tin is considered as a toxic heavy metal. To us human, tin can be very toxic to us. But then we happen to be using tin for most of our food products. Of course, because it has been coated. So they coat the tin with, say, a non-stick kind of paint, so that they cover the paint, the tin from undergoing reaction. Again, don't forget that tin can react with oxygen, form the tin oxide, which is quite toxic. And so if you are going to be buying, of course, tin poisoning is real, but then it's a problem which exists, especially at this part of our world. So if you are going to be buying a product which is a tin related, and that product has been smashed, please don't buy it. If that is the only product that's available, don't buy it. Once yeah, first is the product has been smashed. There's a tendency that the coated surface has been exposed, and so the tin is mixing up with the compounds that are there in the this thing, and then it's going to be harmful to the system. Okay, now if you are going to be buying a product, so basically, for example, say tin tomatoes, the advice is that once you open the tin tomatoes, don't keep the tomatoes in the tin again. Once you expose it, reaction has begun. So you take, if you are using half, you take all the product out into, say, a rubber container and put it in a fridge. But once you open a canned food, you have to finish that, or you just have. I've seen people putting oil on the surface. When you put oil on the surface, what you are thinking about is to prevent the tomatoes from engaging the environment, so that there will be no mold on the tomatoes. That you are preventing or protecting the tomatoes. How about the tin? Okay, so you are not really safe. You are just going to be creating what you call tin poisoning into that food. So we ought to be very careful, and we use tin a lot, not only for canned food. Sometimes sodas, kitchen utensils, you have tin there, and those kind of stuff. So once it's exposed, don't just go. You go to a shop and then you see this, please don't buy it. Once there is a kind of rust anywhere outside the can, there's a tendency that the reaction began from inside the can. So the product inside is not safe for you to eat. So you need to really avoid tin related. Don't say that, oh, it's just the outside. I've seen that people then, for example, if you're going to be buying, you check the expiring date, or what we call the best before time. Can somebody help me? What's the difference? The expiring date and then the best before time, the BB. What's the difference? When we say best before, what is the, and then the expiring date? Okay, so whenever you see the expiring date, meaning the product in that container is not good for usage again. That's what you call the expiring date. Now, the best before date means that the product in that can is not going to be the same. So it's going to be changing, starting the decomposition from that time. So from that date going, that product that is in there is no more that product which you want. But the expiring date meaning it has fully decomposed. It's rather funny that I hear that, of course, this one, you can easily clean it with alcohol. So some storekeepers will just clean this thing with an alcohol and put another date on the can. Or they will quickly sell it fast by reducing the cost. So you go and say, oh, this side they have started reducing things. No, they have started reducing things in the market. They have started reducing things in the market. Please, when you buy, check the expiring date. Okay, so that once there is this decomposition happening, there's a tendency that reaction has also begun. So never eat food that have been indented in cans, and that the package has been broken somewhere, or at a point, I mean, you can see a little bit rust. Yes, Wilson.
Yeah, Doc, please, for 3 months to the expiring date, is this safe for consumption? Because
Yes.
sometimes some people bring some food stuff from abroad, and then you see that the thing has started rusting, but the expiring date is just 3 months to this thing before it will expire.
So the truth is, if there's rusting, then don't
Mhm.
go for it. Once there's rusting, what it means is that the reaction has started inside. However, if there's no reaction but 3 months to the product, then that is okay because it has not fully decomposed. The date that they started there, but it's unfortunate. The Food and Drugs Authority, well, they are now authority, and then the standard board. Okay, so once they separate, I knew that once they separated these two offices, they were going to run into problem. The standard board was going to be checking that all kind of product that gets into the market are standard, including foods. Then the food drugs, or those times they were also like a unit. Now they have their own authority. Are also going to be checking that these products that comes into market are safe. So ideally, they should be going to the market themselves to be checking some of these things, store by store, to be checking. And if the storekeeper themselves should be having agents from the authority to be visiting them, or they will check and then report back to them. So once it has started rusting, don't go for it. But 3 months to the time, you have still not exhausted, except the day or a day before. So if it is BB, that's the best before, then the day before that date is still not okay for drinking. And after that, it's even worse. But then for expiring date, getting to that date means that you are safe. But then after that date, it has broken down completely. Which I'm sure even normal egg that we eat, we should put expiring date on it. But we don't. So you keep your egg for 1 week, then you cook the egg, you see the yolk turning ash. I mean, I saw one the last month that I visited the food. I went to a funeral and then they serve us a food, and then the egg, when you open the yolk, was ash. One professor was pointing to say, so Kushawe Papa no. That means that there is an expiring date to even normal egg that way. But here we don't care. Once somebody can even remove the kind of this thing and then we'll sell it, and people will go to buy it. And I one time chance on one where I drew the woman's attention. He told me that, so I mean telling her that the thing has expired, who will buy it? I said, well, I can't also buy that because I've seen something that will kill me. I will not buy it to go and die. So yeah, so to one and talk, I'm too well. I'm sorry, but I can't buy it. I'll go and buy somewhere. So if an ignorant person will come and buy it and go and die, that's it for him. But I will not see death and go and chop death. But then we play on sympathy and people's conscience. So please, for tin, be very careful how we handle tin products. So we don't just, so I think tomatoes, transfer everything from the can once you open it into a plastic container instead. Okay, so it's quite kind of safe to use aluminum can than to use tin can. But aluminum, so for example, aluminum foil, and those is safe rather than use tin foils and those stuff. It's quite cheap, but then it's quite dangerous because it can cause the tin poisoning. Yes, Aaron.
Doc, please, this point, if you apply it to our spray, will it even work? Because I have I have a spray that I use that's made of tin. I can visibly see it's made of tin. So with that one, we have to throw it away.
I don't get it. A spray which is having the container is tin.
Yeah,
A
it's made of
spray.
tin. So if one way or the other, some part of it is cracked.
So
Uh,
are you injecting it? If you are going to be injecting it, then please don't use it.
on the skin.
And don't, use it, because it's going to get into your skin.
Okay.
And don't use it, because it's going to get into your skin. And don't use it, because it's going to get into your skin. And don't use it, because it's going to get into your skin. And don't use it, because it's going to get into your skin. And don't use it, because it's going to get into your skin. And don't use it, because it's going to get into your skin. And don't use it, because it's going to get into your skin. And don't use it, because it's going to get into your skin. And don't use it, because it's going to get into your skin. And don't use it, because it's going to get into your skin. And don't use it, because it's going to get into your skin. And don't use it, because it's going to get into your skin. And don't use it, because it's going to get into your skin. And don't use it, because it's going to get into your skin. And don't use it, because it's going to get into your skin. And don't use it, because it's going to get into your skin. And don't use it, because it's going to get into your skin. And don't use it, because it's going to get into your skin. And don't use it, because it's going to get into your skin. And don't use it, because it's going to get into your skin. And don't use it, because it's going to get into your skin. And don't use it, because it's going to get into your skin. And don't use and that is going to get into the body. So you just have to avoid that.
Okay.
Now, I think we used to have tin-related pesticides, like what was the name, Maxam, and because of that, we then switched to the polymer this thing again. So I don't know if we still have this type of toothpaste that have thin, kind of very very hard kind of this thing, but and now I don't see them. Maxam when we're just so this was when you brush your teeth and you still feel some bleaching thing on your teeth. That's just that. But for thing we use in soda, the cooking utensils, like the stainless steel, we have tin there, the roofing sheets, the cans that we have, batteries coated or the tin cans, and then these lanterns that we no more see them again. This thing, we no more see them again because now we don't have kerosene, much kerosene at use. But then they are also there, so we have a lot of them. I should say that biologically we don't have any use for tin. But what you know is that the metallic tin can be poisonous in that it can be poisonous. The metal tin itself is not, but then when it becomes a compound, so tin, organo tin is poisonous and must be really handled with care. Okay, we should really handle that with care. Yes, Arthur. So that
Doc,
yes,
please, I want to ask you, aside the tin, you see, when you buy the tomato paste, there is a layer, something like a foil layer in the tomato paste. That one, do you have a tin composition to that particular package?
that's the coat. That's the coating to avoid the tin engaging the product.
Okay.
And it's a
No,
coat.
the
So some
coating,
use
that coating, yeah, that coating, is it a tin, that particular shiny surface that you see when you open the tomato paste?
no, I don't think so. So if we have such, then I'm thinking that should be more or less like aluminum related, not tin. But then I know they coat the tin with this epoxy so that the tin will not be exposed. So they paint with epoxy. So that's why I said when there's a smash means the epoxy is broken. So the tin now is exposed. So the shiny surface there will not be tin. Okay, Aaron, a quick one, then I'll just summarize it. And
Okay. But please, the roofing sheet,
yeah,
has it been switched or they still use it for the roofing sheet?
no, it's no more in use now.
Oh, okay.
It's no more in use now. The roofing sheet that we use is zinc aluminum. So either they are using zinc or they are using aluminum or the mixture, what they call the aloe zinc, aluminum and zinc. But the thin roofing sheet is no more common. It used to be common in the villages, but now I don't think we're using tin roofing sample.
Now, please, one more question.
Okay.
I want to
Yes, I
ask
can
you,
hear you.
uh-huh. You see, the ladies, some of the females, when they don't want to give birth and they're using a protection, there is something, the birth control injection or some metal they place within the body. I don't
The
know whether
IUP.
that metal,
You mean IUP?
yes, yes,
It's
what
not a metal.
uh, okay, okay.
Uh,
I thought
it's
it's a metal.
no. Some are rubber, some are even hormones related. But of course, maybe because it is hard, that's where um what's a please can somebody what's the full name? Is it IVP or um
Intra-uterine device.
they call it what?
Intra-uterine device. intrauterine device.
You're the person speaker. Santi, your voice is far. I can't hear you.
It's called intrauterine device, IUD.
IUD, not IUP. Yes, the device. Yes, and some of them are quite. So it's not like a metallic sound. I mean, some are rubbers, some are hormones related, and those kind of stuff. Okay.
Hello, guys.
Yes.
Hello. So I have a question. I have an non-stick, but the inside, it has it has it has started peeling off. Does it have effect if I boil or if I cook inside?
Come again. You have what?
I said non-stick.
Yes.
My non-stick, yeah, the inside, it has started peeling off the paint, let's say the coat. It has started
Oh
peeling
yes.
off.
Some of
So
the
if I still boil or cook inside, does it have effect?
yes, the utensil itself may be coming from aluminium. But then the problem is the non-stick itself, the epoxy that they use. The epoxy, once it gets broken, it releases the compound. So any heat, when you apply the heat, the epoxy that was used in coating will now be, will be decomposing because you are exposing it to the heat. So once it kind of starts this, and of course, definitely there will be an issue. But then I have not really read whether the effects, but definitely because it has been exposed and heat is now getting used to it, there's going to be a problem. And the epoxy there is the PTEE and PTFE. That's a polytetrafluoroethylene. That's what you call non-stick. So once it has started peeling off, meaning it has started decomposing, and any heat will begin making it harmful. So especially if you are using heat more than 100, 200 degrees, the boiling point or the melting point of that polymer is around 250, 60 degrees Celsius. So if the temperature is that quite high, it means that it will become harmful. Uh, we science is so funny. We solve a problem by creating another problem. Okay, so instead of washing our cooking utensils, we'll create a polymer which will make us reduce the washing our cooking. So for non-stick, we don't use foam or washing this thing to wash it. Just a liquid soap, and don't use detergent because detergent is strong enough to react with the polymer. So use a liquid soap, a mild liquid soap, so that it will not, and you don't use brush to scratch the surface. Once the surface begins scratching, and that is why when you buy that, the recommendation is that you use a rubber ladle, not a metal, to be scratching the surface. But sometimes we'll put the rubber somewhere, we use a spoon to be scratching that. So once you expose that and you apply heat, I'm sure it's just definitely going to be kind of harmful. And so that's a toxic. The non-stick for you is going to be toxic. Okay. So we'll meet tomorrow. When we meet tomorrow, we're going to be looking at lead, so that gradually we'll just be making a way for it. Please, any other question? Please, any question?
Hello.
Okay.
No,
Okay.
please.
So thank you for your time. See you tomorrow at 12.
Hello, sir.
Okay, Doc.
Yes, sir.
Hello. So the network was good. So what you said right now, I didn't hear.
Please come again. I also cannot hear you,
Hello.
Christopher.
Yes. Yeah, I said you said something right now, but because the network was not good, I couldn't hear.
What I said right now is that we'll end the class now and then we'll continue tomorrow.
That is tomorrow. This thing to do is online.
Tomorrow at 12 p.m. online, yes. Please, this class is for online class. So if you are joining this class and you are not part of the online class, we know we have 2 centers plus an online kind of this thing. So if you are not part of and so I think the centers is West Square, West School, and then which part?
Ghana.
Hello, Doc.
West Square, Ganas.
Hello,
But
Doc.
apart
UCC.
from the
UCC.
West uh, West Coast UCC, and then Ganas. Those in the northern part, and these are the ones that are supposed to join the online. So if you are just here as an intruder.
Oh.
So if you have a center, then you are not supposed to join this class.
Okay.
So it's just like a 206. If you have the online, then we have centers. So tomorrow, 12 p.m. is for online. It's not for those that are meeting the centers at the centers. This over, are you okay? Okay, so I can see Christopher is an intruder. Emmanuel Asante is also an intruder. I can clearly see. Okay, so see you tomorrow.
Okay, Doc. God willing, tomorrow.
Thank you, Doc. Sir, please, I'm Ghana Center. Okay, sir.
So the class is ended, Ima. The class is ended. Doctor is out of the way.